Good. Hello, everyone.
Okay. Hello, everyone. Welcome to Crypto Cafe for the fall 2025. Today, we are happy to have Hansraj, who is a PhD student in the Department of Mathematics and Statistics at FAU. Prior to studying his doctoral studies, he worked as a JRF at DRDO in India. His research interests include lattice-based cryptography and quantum algorithms. And today he will be talking about a quasi-polynomial quantum algorithm for EDCP over power of 2 moduli.
Thank you, Dr. Das, for the introduction, and I'm sorry for the delay. And today I'm going to talk about quasi-polynomial time quantum algorithm for EDCP over power of 2 moduli. And this is joint work with Sibai, Elena, and Tran, and William. So before looking at the algorithm, I want to talk about a little bit motivation behind this algorithm. So we all know that how LW is really important in lattice-based cryptography or in post-quantum crypto schemes, because most of the NIST standardized schemes are based on LWE. And we were trying to figure out the hardness, quantum and classical hardness of learning with error problem, which was introduced by Regev in 2005. So to understand the classical and quantum hardness of LWE, so classically, to look at the hardness of LWE, the first approach is about lattice reduction algorithms, and for the quantum to check the quantum hardness of LWE, since we know that this LWE problem reduces to DCP, which is like dihedral coset problem, or we can also say dihedral hidden subgroup problem, which was introduced this reduction was given by Regev in 2002 and 2007 works. So if we are able to understand the hardness of dihedral coset problem, that will give us some idea about the hardness of LWE. So the motivation of this talk will be looking at the hardness of dihedral coset problem, and particularly not just dihedral coset problem, we will look at the EDCP, extrapolated dihedral coset problem. Since in 2018, in BK's the blue paper, they gave a reduction from LWE to EDCP, and they showed that these two problems are equivalent. So if we are able to figure out what's the complexity of EDCP, that will definitely help us to get some ideas about the hardness of LWE. So yeah, the question is, what's the complexity of EDCP, extrapolated dihedral coset problem? So that's the motivation of the talk. We will introduce all these problems, and then we will look at our algorithm. So in this talk, we will introduce a quasi-polynomial time and sample quantum algorithm for EDCP. EDCP is extrapolated dihedral coset problem. So before going to DCP, EDCP, I want to introduce LWE, learning with error. So in LWE, what we have, we are given the samples of this form, AI and BI are generated as AI times S plus EI. And AIs are uniformly distributed in GQN, and EI are normally we take as Gaussian distribution. Suppose we are given these samples, we want to find the secret S. So it really depends on the parameters of LW, like N, Q, and alpha. Suppose alpha is equal to 0, we will not have any error. In that case, we can solve this LW problem by just Gaussian elimination in polynomial time. But if we choose error from discrete Gaussian distribution, in that case, LW is particularly hard. So this is the search version of LWE, learning with error. We can also think this as in the matrix form, like we are given a tall matrix A and a column vector B, where B is generated as A times S plus E, and we want to recover the secret S. And here, rows of A are uniformly distributed in GQN, and EIs are discrete quotient distribution. So the hardness of LWE really depends on the noise and modulus ratio. Noise, EI is the noise in our problem, and modulus is Q here. So if alpha, as I said, alpha is smaller, then we can solve this problem in polynomial time by using like Aurora-G kind of algorithms.
Sorry, what is sigma?
Sigma, so alpha Q is the like width of standard deviation of our EI. EI belongs to Gaussian distribution, and sigma is the standard deviation. And in standard LWE, which is assumed until now, it is computationally hard. In standard LWE, the parameters are Q is equal to polynomial and M is n log Q, and this chi, okay, so the chi is this D here. Chi is the distribution for EI, which is discrete Gaussian distribution with alpha Q standard deviation. And the complexity of this problem for this standard parameters is exponential, and alpha Q is approximately big of square root of n. And since we have like worst case to average case reduction, this problem reduces to SVP with approximation factor around like polynomial or square root of n. So that is one of the reasons people are more reliable on lattice-based cryptography, because we have this kind of worst case to average case reductions. And as I mentioned, our algorithm works for extrapolated dihedral coset problem. So first I will introduce dihedral coset problem. So in dihedral coset problem, it is like quantum version of hidden subgroup problem for dihedral groups. And in this problem, what we have is we are given these quantum states of this form, like 0, xi plus 1, xi plus s. And here this modulus n, capital N, is exponential. And suppose we are given these samples where si is fixed through all these samples and xi are the uniform in Gn, and we want to find the secret s. And this is the dihedral coset problem. We can think this as dihedral hidden subgroup problem. Hidden subgroup problem, if you guys know, hidden subgroup problem is, if I just quickly mention. So for the dihedral case, Tn, hidden subgroup problem for dihedral groups is, suppose we are given a function f, we can think as a black box from Dn to some set S, some finite set S, and we know that this function is constant on a subgroup of Dn, on a subgroup of Dn. So in that case, finding, like, we don't know anything about this function, but we know that this function is constant on this subgroup, on this H subgroup. Finding this H from Dn is called as hidden subgroup problem for dihedral groups. So in dihedral groups, mostly like the subgroups of this form, like identity and R to the power n s. So these are the non-trivial subgroups of dihedral groups. So we can think as like this let's say this is x. So this x is the secret, because all the subgroups are of this form, R to the power x s. So this x is somehow will be transferred here as s in the quantum version of this dihedral coset problem. So that's the basically intuition behind dihedral coset problem, and this is computationally the best algorithm for this problem is sub-exponential, and it was introduced by Kupperberg in 2005. Let's look at the example of dihedral coset problem. Suppose n is equal to, capital N is equal to 8, and our secret is S. So when we are given a quantum state of this form, let's say first state is 0, 1 and 1, 4, like 0, 1 and 1, 4. This is the quantum state we are given, the one sample of DCP problem. Let's say the second sample is given as 0,3 and 1,6. And third sample is given as 0,7 and 1,2. And now, once we measure these samples, like these three samples, once we measure them, suppose, since if we are given a state of this form, when we measure it, the probability of getting output 0, 1 and 1, 4 is equal because we have a normalizing factor which is 1 over 2. So when you measure this quantum state, you will get either 0, 1 or 1, 4 and with equal probability, with the probability 1 over 4. So once you measure these three samples, suppose you get 0, 1 and 1, 6 and 1, 2 because we have equal probability. And after the measurement, these outputs doesn't reveal any information about our secret when capital N is exponential. So this problem, this EP problem, the best algorithm until now is sub-exponential by Cooper. Yes.
Sub-exponential quantum type. Like
yes, sub-exponential quantum type. Yes. We will look at the algorithm. I will quickly look at the algorithm on DCP, then we will go to the algorithm on EDCP because our algorithm also have a very similar idea as the Cooper algorithm. And now I want to introduce the EDCP, extrapolated DCP. By the name of this problem, extrapolated DCP. So here, our xi and s are the integers. They belong to Zn. So EDCP was introduced in 2018 in BKSW paper. So what they did is, what if we increase the number of Septs? So here we had only 2 Septs, but here we generalize the number of Septs from 2 to we can go until like whatever we want according to the distribution m number of Septs. And the other thing is here these xi are the vectors. So we generalize the DCP problem in number of Septs and also in the dimension also. So that's why we have here like 4 different parameters. So here we had only 2 parameters, capital N and small l. L was the number of samples and capital N was the modulus. And here we have 4 parameters where small n is the dimension. Now xi can have like n dimensional and s is also n dimensional. So n is the parameter, q is the modulus now. So here we had modulus n and here we have modulus q. So the randomness of secret is kind of here like n to the power q. So we can think as like, yeah, these problems might be equally hard because here the modulus is capital N, which is exponential, and here the secret S has like, it comes from a set which has a number of elements n to the power q. And we have like some connection between LW and EDCP. And here we had like uniform distribution. So when I'm writing here, this is not correct. We have 1 over square root of 2, then only it is well defined. So here we can replace this with any distribution, DJ, which is discrete distribution. So, and the most common distribution for EDCP in that paper they considered was Gaussian distribution, discrete Gaussian distribution. And if our distribution is discrete Gaussian, in that case we call it GEDCP. And if our distribution is uniform, in that case we call it UEDCP. U means uniform here. And if n is equal to 1, if our distribution is uniform, n is equal to 1, and capital M is equal to 2, then this is just exactly DCP instance. And we have like GEDCP and UEDCP are computationally equivalent. We have reduction between these 2 problems. And we will focus on particularly UEDCP.
They're equivalent for any distribution or just
only for these 2, G and Gaussian and uniform.
Oh.
Yeah. Only these 2 distributions. And we were particularly interested in those 2 distributions. Yeah. So first before going to the algorithm, so let's look at the relation between LWE, DCP, and EDCP. So in 2005, Regev gave some reduction from LW to DCP. And in 2018 paper, there was a reduction from LW to EDCP, but this is very important here. We have some restriction. So, okay, the other things like, so when I say a reduction from A to B, when I say a reduction from A to B, it means if we can solve problem B, then we can solve problem A. So we can say that A is not computationally harder than B. And it really depends on the, suppose like this problem had parameter n and q, and this has m and x. So it really depends on how parameters changes also. So in this reduction, so we have an algorithm for EDCP which works in quasi-polynomial time, but we don't have algorithm for LWE because there is some restriction because of this condition. And we have a reduction other way around also, EDCP to LWE. There is slight change in the parameters. And also we have a reduction from EDCP to DCP also. And this work will focus on EDCP. There is algorithm for EDCP. Yes.
So that means we also have a worst case reduction for EDCP problem, right?
Worst case.
We have a reduction, like worst case reduction for LWE.
Mm-hmm.
It means we have a worst case reduction for EDCP.
Yes, we can say, because ADCP to LWE and then LWE to SVP.
Okay.
Yes.
Okay, let's continue.
Okay. Yes. So first, I will introduce a little bit about the Kuperberg's idea of solving DCP. So Kuperberg introduced algorithm for dihedral coset problem, which is an instance for EDCP. So in that algorithm, what he did was, so this was the one of the sample of dihedral coset problem 0, xi plus 1, xi plus s. So what we do here is we create samples of this form. And how we do it, we apply QFT on second register and then measure it, and we get a state of this form. And when we measure, we get the value of y classically. We will know y classically. So once we have these kind of samples, I will explain in more details like how we can get these kind of samples. But this is the idea. Once we have these kind of samples and we know y, then we will combine these samples somehow and we will try to create a state which will help us to reveal the last bit of secret. So that's the state we want. If we, since like this y is known, and when we combine, it will somehow like if you combine two states, we can make the entries of y equal to 0, and somehow if you are able to create a quantum state of this form, once we have a quantum state of this form, we can get the last bit of secret S, because once you measure in the Hadamard basis, that will reveal the last bit of secret S. So it's kind of like BKW kind of algorithm. It's very similar to BKW kind of algorithm where we are given like yi is vectors and we are combining them, and since n over 2, suppose capital N is 2 to the power n, capital N is so we want somehow combine these samples such that we get y is equal to the power n minus 2. Because once we have y is equal to the power n minus 1, then we will get this state. Because omega n, that will just like, it will just become -1. So yeah, this algorithm runs in sub-exponential time and sub-exponential samples. Okay, so I will introduce this algorithm, but the main tool for this algorithm is quantum Fourier transformation. it is like analog to classical Fourier transformation. So it can be defined as, suppose we are given a register, and if you apply QFT over GQ to the power n, then it's just like, it's like summation y to the y belongs to GQN, and it's like we have a linear transformation with that discrete Fourier matrix, like one omega omega square and all stuff like this kind of matrix. So it's, we can think, so this QFT is a quantum circuit which can be represented by a linear transformation, and it's like we are multiplying by a matrix which is of this form. One omega square omega. So yeah, something. So it's similar to discrete Fourier transformation. It's only the difference is in discrete Fourier transformation we apply on a vector, and here we apply on a register. And this is the example. If you see QFT on 0, 1 is equal to 0, 0 plus, because because omega 4 0, 0 times 0, 1 is just 0, so that's why we have here 1, and similarly, like omega 4 is high, and similarly we can figure out everything. Any questions? So the Kuperberg's algorithm is like, we are given these quantum states, DCP samples 0, xi plus 1, xi plus s mod n, and where s is fixed through all these samples, and xi are uniformly distributed in Gn. So the first thing that it did was apply QFT on the second register. So by just looking at the definition of QFT, quantum Fourier transformation, if you apply QFT on the second register, that will give us this following state. The first register is as it is, and on the second register, we apply QFT, so we'll have y, and since we are applying QFT, so the QFT over Gn, so the summation will run through y belongs to Gn. And that's just like the definition, how the quantum Fourier transformation works. Okay, and if we measure the second register, okay, so there's one thing. Suppose we have a quantum state of this form. F of x, suppose x is equal to 1 to n. So now if we measure this like when I say I measure the second register of this quantum state, so what will I get? Suppose once you measure this, you will get, suppose fx is equal to b, some value b. Then the output after the measurement we will get as x is equal to 1 to n, such that fx is equal to, so yeah, those x such that fx is equal to b. So that's the measurement. Like once you measure the second register, we will get a quantum state of this form. Suppose the function f of x is seems like this one. When x is equal to 1, 2, 3, the output is b. So in that case, we will have a output state as this one. So it will collapse on those values where function is equal to the measurement output. Does it make sense? Okay. So similarly, if we measure the second register here, that will output as this following quantum state. And once you measure it, the y will be known classically. So we know the value of y, and we know this quantum state. So after the measurement of the second register, we have this quantum state as well as y is known here classically. Okay, now So one DCP sample can be converted as this, we call it as a phase sample, where like phase sample is Y and this quantum state. Now, if we do for two DCP samples, we will get two these kind of quantum states. And if we tensor these quantum states, we will get a quantum state of this form. So tensoring to quantum state is similar to tensor to vectors. So when I say like, so if I just give a simple example, 0 tensor with 1. So this is just like tensoring these two vectors, column vectors. So this will give us 0, 1 and 0, 0. So similarly, if you tensor these two states, psi y1 and psi y2, we'll get a quantum state of this form. And the next step in this algorithm is we apply a C0 gate on the second register. And C0 gate is defined as, suppose we have X and Y. If you apply C0 on the second register, that will give us X plus X XOR Y. So if you apply C0 on second register, we had like 0, 1 in the last. So we had 0, 1 and 1, 0. So 0, 1 will be exactly 0, 0 will be exactly 0, 0. And 1, 0 will become 1, 1 because we are applying C0 on the second register. And 0, 1 will be exactly 0, 1 and 1, 1 will become 1, 0. So we will get a quantum state of this form after applying C0 on the second register. And if you see here now if you, okay, yes. So now if you take first one and the last state, that's just exactly psi y1 plus y2, comma 0. And if you take out omega s y2 from like these two, if you take out, then we will get a psi y1 minus y2. Yes, it's just like rewriting, and we know the definition of psi y1, psi y. The definition of psi y is just this quantum state. So when I'm saying psi y1 plus y2, it means 1 over square root of 2, 0 plus omega y1 plus y2 times s and 1. So just rewriting this quantum state will give us the following quantum state. And once you measure this one, you will get either psi y1 and psi y1 plus y2 or psi y1 minus y2. And we know that psi y1 plus y2 is of this form, or like y1 minus y2 is also this form. So our target was to combine the samples and get something like y is equal to 2 to the power n minus 1. So that's the idea of Kuperberg's algorithm. Suppose y is a binary, like binary string of n digits, suppose b1, b2, bn. So what they were doing, they were clearing the square root of n bits after combining like two samples, and then going to the next square root of n bits. And that's why the complexity is 2 to the power square root of n. So if I be more precise, so our n was 2 to the power small n. So if we take a binary string, and importantly, the bits of this strings are uniform. Like these BIs are uniform. So if you take like 2 to the power square root of n many strings of this form, there is a good probability that we will find the matches in last square root of n bits, because all the binary strings are uniform. So that's why the complexity is 2 to the power square root of n. So they were clearing the square root of n bits at one time and then going to the square root of n next bits, and somehow like in the end they want a string of this form.
This is a consequence of the Bartre paradox, right?
Yes, yeah, like the collision between if we have
The collision.
yes. So yeah, so that's the and why they were doing square root of n, because if you take less than square root of n, then you will need more number of samples, and if you take like in both the square root of n is the benchmark where you get the best time complexity to the power square root of n. If you go a little bit higher, then you will need more samples. If you go a little bit lower, then you will need more steps, more number of steps.
I agree.
Yes.
What does the collision represent exactly?
Collision means the last square root of n bits are same. Suppose like here,
As far as
like suppose this last 4 bits.
I mean, as far as the overall problem, what are we saying? When we get a collision, we get a subgroup, or like, what are we talking about?
So what we are talking about, so once we combine these two states, we can get a states of this form like psi y1 minus y2. And y1 and y2 are known classically. Y1 and y2 are the numbers, suppose like
You solve the problem if you get a collision, is that correct?
yes, because if you have a collision, then we can clear the bits and we can get a state of, like we can get a y of this form, and that's just like 2 to the power n minus 2, n minus 1. That's 2 to the power n minus 1. So yeah, the idea is like we are clearing the bits in batches, and the batch size is square root of n. And since the binary strings are uniformly distributed, you need initially 2 to the power square root of n samples. And once we have 2 to the power square root of n samples, we can find two those y's which have like last square root of n bits are same, and we can combine them, and we can continue the procedure.
So, like, so what is the current challenge? Like to reduce the number of samples?
To reduce the number of samples or number of the Kuperburg algorithm is like 2 to the power square root of n number of samples as well as time. It's the same. Because when you have those number of
You
samples,
have to check everyone. Say
Yes,
like
yes.
2 to the
Yeah.
square root n many samples. So just you check it. So your time complexity is this, right?
yes,
And they are all binary.
yes, they are all binary. Yeah.
Okay, continue.
So that's the idea behind Kuperburg's algorithm. And here, yeah, as I was explaining, that since we know y1 and y2 classically, our goal was to combine, use this combination procedure and create a state of this form. And once we have a state of this form, like if you measure this into Hadamard basis, that will give us last bit of secret S. So, yes. And I don't think this is difficult to see how we can get the last bit of secret S here. Once you measure in the Hadamard basis. Okay. So, okay. Yeah, so now I will give outline of Kuperburg algorithm and our algorithm for EDCP. So in Kuperburg algorithm was for DCP, but DCP is just EDCP in one dimension and M is equal to 2. So in the first step, we were given these coset samples. The only difference here is in the DCP, we have the xi's are just integer, and in this problem, we have the vector form. That's why we have n here. And the first step is the same for both the algorithm. We apply a QFT on the second register and then measure, and then we create these samples. So we have a sample like we know Y classically and we have a quantum state, and we call this as a UEDCP bar sample. So if we are given a UEDCP sample, we can create a UEDCP bar sample. And so the only difference between Kuperberg algorithm and our algorithm is, in Kuperberg's, they combine two samples. And then they got like psi y1 minus y2. But in our algorithm, what we do is we combine more than two samples. We combine n plus 1 samples. So when you combine n plus 1 samples, we will get a state of this form. So, and why we are combining n plus 1 samples, there is a reason. Since the dimension of vector is n, and we are combining n plus 1 samples, so that we have a solution of this linear system, because now y is n times n plus 1 dimension. So we will have a solution of this linear equation, and we can continue the algorithm. So, and this idea is not new, like combining more than two samples was used by Regev to reduce the quantum space for this Kuperberg's algorithm. But he was solving a hard problem after this procedure, like a classically hard problem, which took some exponential time. But here we are not solving classically hard problem. We are just doing the linear algebra. And in Kuperberg algorithm, we recover last 1 bit only, because after this procedure we get only 1 bit. But in our algorithm, since secret was a vector, so we will recover last bit of each entry. And that will, it means like we are recovering n bits at one step. Okay, so yeah, this is the main step of the algorithm. So we are given a UEDCP bar sample, and we are combining n plus 1 many them, and we are getting one sample with, here the modulus was q, and here the modulus is q over 2. And that's what in Kuperberg's algorithm they were doing, like they were reducing, but their modulus was exponential, so it was a little bit different, but somehow we are reducing from q to q over 2, and suppose q is 2 to the power n, 2 to the power suppose t. So if we follow this procedure, then we can go to until 2, and that will give us the state we want in the end. So how we can do it? So first of all, we will tensor n plus 1 many these UEDCP bar samples. So when you tensor n plus 1 many UEDCP bar samples, we will get a quantum state of this form, omega q, and where this y, capital Y, is n times n plus 1 matrix, and this y is known classically. Since in UEDCP bar sample, we were given this y, yk, and this quantum state. That was like these two things were given, and now we are combining all of them. We get a quantum state of this form, and where this y is known classically, and also yi's are the uniform in GQN. The column vector yi's are the uniform in GQN. The next thing is, yes, so next thing is like we compute y times j mod 2 in new register, and then we measure the second register. So again, the same phenomena like here, like if you're computing this function, once you measure this, that will collapse on those j's, which are the solution of this equation. And here, the thing like yi's are uniform, that will help us here, since like this matrix Y, which is of dimension n times n plus 1, has full rank with constant probability. And it is because the columns of this matrix are uniform mod 2. If they were not uniform, we cannot say, but they are uniform, so we can say that it has a constant probability that this matrix has a full rank with constant probability. Like this matrix has a full rank with constant probability. And this matrix is dimension n times n plus 1, so it will definitely have exactly two solutions. This system of linear equation have exactly two solutions because we have one free variable. So now what we can say about this state, what we can say about this state. So this state was like j belongs to this one, such that y times j is equal to p mod 2. So this state, this has only like two, this is just like superposition of two states because we have only two solutions. Like this system of linear equation has only two solutions. So this state exactly looks like this one, where J0 and J1 are the solutions of this system of linear equation. And if you take out the global phase, you can rewrite this as, since like if you take out y omega q, y like this amplitude, that will give us this quantum state.
What if it's 0 and 1? There is not J0, J1.
Okay, so yeah, like I'm again not considering the normalizing factor, but it's just like, so we had this, so if you take out omega q, y j naught comma s. Oh, okay, so you are saying,
Yeah.
okay, this is change of basis, like we can do it just like renaming the basis.
Oh, okay, it's just a really bring up.
Yeah, just renaming, yeah. Sorry, I was thinking you are asking about the.
No,
Yes. Yeah, it's not just like we are ignoring the global phase and renaming the basis also.
Yeah.
Yes. Okay. Now, the interesting thing is, since like J0 and J1 are the solutions, so y J1 minus J0 is 0 mod 2. Since y J0 and J1 are the solutions, so y J1 is B and y J0 is also B, so y J1 minus J0 is 0 mod 2. So we can say that this is just equal to this one, where y prime is equal to y J1 minus J0 divided by 2. So we somehow reduced out from Q to Q over 2. And that's what we wanted in our, like the main step we wanted from, like we wanted to combine n plus 1 many samples, and we wanted to reduce the modulus from Q to Q over 2. Okay, so now if we continue the procedure, we can go until like Q over Q over 2. That will give us modulus 2. So if you follow this chain of steps, chain of combination steps, we can go from like Q to Q over 2, Q over 2 to Q over 4, Q over 4, and then until like we get 2. And now that's the, like, there is no much math to compute the complexity of the algorithm. Since every step needs n plus 1 many samples, and we have log q many steps. So initially, if we have n to the power like peak of log q, then in the end, we will get n many samples with the new modulus, which is equal to 2.
How is Q and N related?
Q and N related. I don't think there is any relation right now, but in the complexity, because at one step we need n plus 1 samples, and we have like log q many steps. So like if we start with n plus 1 to the power, like if we write exactly, it should be around like n plus 1 to the power log q.
I see.
And if you put big O. So these many, if we start with these many samples, like we will get in the end n many samples with the new modulus 2.
But you wrote there that n to the log q is basically 2 to the log square n, so there must be a relation between q and n. right? So like log Q at least is the legal.
So Q is polynomial. Q is polynomial in N. Yeah. So
Okay.
yeah, Q is polynomial in N. Yeah, you're right. Yeah, Q is polynomial in N hour.
I see.
Yeah, that will.
So the logs are comparable up to a constant.
Yes, yes. Yes, you're right. Yeah. Okay. And the final stage looks like this one. And again, now we have, in the Kubernetes, we had just like integers, but now we have the vectors here. Y, K, and S are the vectors. And since in measuring Hadamard basis will give us pi k times S mod 2. And if we have n many these equations, then we can get the last bit of secret S. By just doing the Gaussian elimination, it's just yk times S, like y1 times S, y2 times S mod 2. By just doing Gaussian elimination, we can recover the last bit of secret S. And we can continue the procedure by just shifting the entries of secret S. Now, so the one step of this algorithm will give us the last bit of each entry of secret S. Now we can just like compute this in new register because S bar is known. S bar is S modulo 2. So if we compute this in new register, and that will be our new EDCP state. And after like converting this into UEDC bar, so we will follow we will continue the algorithm for now these kind of samples where we already have Q over 2 and S prime is just like shifted bits. So we are now in the next step, we will focus on the next bit of next last significant bit of secret S. Okay, and if you see here in this whole procedure, I mentioned that okay, in EDCP we generalize the number of shifts and we generalize the dimension also. But in this algorithm, we were considering m is equal to 2 only. The number of shifts is exactly same as in DCP. But we have a reduction from UEDCP. So if you can solve UEDCP for smaller m, you can solve UEDCP for any m. So solving UEDCP for smaller m is more difficult. So using this reduction, we can say that we have a quasi-polynomial time algorithm for any m. M was the number of shifts. Capital M was the number of shifts. So this is the main result. And now we can quickly look at the application of this algorithm. So because our intention was looking at the security of LWE, what's the quantum or classical security of LWE? So the first thing is like in 2022 they defined a problem SLWE, which is like quantum version of LWE, where we are given a quantum states of this form, and again like we want to find the secret S. This was like first time introduced in CLG paper 22. So our algorithm applies to this problem, and because of this reduction, we have again chain of reduction from SLWE to GEDCP, GEDCP to UEDCP. So we can say that we can solve SLWE in quasi-polynomial time with given quasi-polynomial number of samples. Yes.
5 minutes.
Yes. Okay, last thing is what's the impact on LWE? That's the most important, interesting thing I would say. So we have a reduction from LWE to EDCP. So, and we have algorithm for EDCP, UEDCP, which is quasi-polynomial time. But here the important thing is we have another restriction on number of samples. L should be smaller than 1 over m times alpha times polynomial n. So for the standard parameter of LWE, this L, we will get L is smaller than polynomial. So this reduction works For standard LWE, only like this reduction produces only polynomial number of samples for standard LWE. So we cannot say that like we can solve LWE in polynomial time, in quasi-polynomial time through this reduction, since we have a restriction on number of samples for this reduction. Yeah, our algorithm needs quasi-polynomial number of new EDCP samples. Yes.
There are some algorithms. I don't remember, but I know there are algorithms where you don't need to restrict the number of samples for the reductions. But it kind of goes to some other problems, not these EDCP problems.
Yes, because like this is the probabilistic reduction. So if you increase the number of, if you want more number of samples, then you will get with negligible probability, like to the power negative 128. So yeah, and like people try to improve this this reduction, but still like it's not easy to.
Then either you have to make exponentially many samples, or you have to make the probability negligibly small.
Yes. Mm-hmm.
I see.
Yeah, like that one of the open question. So like our algorithm is quasi-polynomial in time and quasi-polynomial in samples. So the first thing is, can we make some trade-off, like making time more like sub-exponential and just reducing the samples? Or can we improve this reduction, like for, like this is polynomial reduction, can we do a sub-exponential reduction which produces quasi-polynomial number of samples? So yeah. And so our algorithm does not extend to standard LWE. There is no impact on standard LWE. And also like we have other way, also we have a reduction other way. Okay, yeah. So that's the complexity. So the EDCP problem was easy for like when M is equal to Q over C, Q minus C. So in this regime, the best algorithm were sub-exponential or exponential, but our algorithm applies for all this regime, and it's quasi-polynomial, and it beats in this particular regime where other algorithm needs sub-exponential samples or sub-exponential time, but our algorithm needs only quasi-polynomial time or quasi-polynomial samples. And these are the future questions.
Okay, awesome. So any questions online? Any questions from here? Any questions from the audience? Okay, sounds there is no question from the online members. So let's thank Hansraj for his talk, and let's meet next week for 2 more interesting talks. So see you people next week.
Thank you.